Good morning, everyone. I am going to start the class on the topic fluidized bed reactor. Actually, all we know that the chemical process industries involve various transfer operations where solid fluid contacts are essential, and whether it is mass transfer operation or heat transfer operation, absorption, adsorption, or any that is synthesis or the mixing process, everywhere the solid fluid contact is required. And here we can, this solid fluid contact or these transfer processes we can categorize or we can handle in, usually we handle in three types of the beds: packed bed, fluidized bed, and semi fluidized bed. In the packed bed, the we can see just from the schematic diagrams, the bed materials remain packed, that is only the void space among them will be minimum, and a perforated grid plate will be there to support the bed materials, and the fluid will be supplied from the bottom. In the fluidized bed, fluidization means the solid, it is the tendency of the solid particles to behave like fluid, where the properties of the solid will be similar to the properties of the fluid. And in this situation, the solids are in the flowing conditions or in the movable conditions, where the fluid is supplied from the bottom, and the grid will be there at the bottom of the bed materials, which to support the solid particles. And in the semi fluidized bed, you can see from these schematic diagrams, a grid is there both at the bottom as well as the top. Here the top, a partial packing condition is resulted, that is bed materials are packed to some extent, it is packed on the top, and in the bottom layer the particles will be in the fluidized state, where the fluid is supplied from the bottom. So, all the transfer processes, transfer operations are carried out either in the packed bed or in the semi fluidized bed or in the fluidized bed in the chemical industries. Now, if you see, or we can categorize this also in the two phase systems, these operations in the two phase systems or the three phase systems. Three phase system example is the semi fluidized bed, where the liquid, solid and the gas, usually air, are there. And in the two phase situations, that is the it may be the fluidized bed, three phase also fluidized bed, three phase fluidization is there, and in the packed bed it is only two phase. And if you see that the operations, whether it is the fluidized bed, packed bed, or the that is semi fluidization, it may be the batch type reactors or the continuous type of reactors can be in the use. Also, depending on the type of the reactions to be carried out, it may be catalytic or may be non catalytic reactors. Now, we should have just idea about the reactor, what are the basic components for this fluidized bed reactor. From the figure we can see that the bed materials are there, which are in the usually the packing, it may be the inert material or it may be the solids which are to be reacted, or in the catalyst particles also may be present here, and the fluid which is supplied, it may be air or may be the reacting gas may be supplied from the bottom also. We should know the what are the basic components of the fluidized bed reactor. Here the bed, the region above the bed is known as the freeboard region, and the bed where the particles are contained, or first initially the fluidized column is filled with the bed materials, and that material up to which the in the before fluidization occupy, that is known as the bed, that region is known as the bed. And here if the heating cooling is required, that way accordingly arrangement to be made to carry out the reactions. And the in the when the fluidizing medium that is the gas or the air is supplied, and sometimes the gas might be the reacting gas we may supply sometimes whenever required, but for continuous fluidization some air is to be supplied from the bottom. Now, when the particles fluidize, reaction may carry out within the bed or in the freeboard region also, and when the reaction is carried out in the freeboard region, the particles which are lighter or whose terminal velocity is less than the settling velocity or the terminal velocity of the particles, that means lighter particles, they move up and they are collected in the cyclone separator, where it is separated from the product gas. As the reaction continues in the bed region as well as in the freeboard region, here the products also product gas along with the some products solid products may remain in the freeboard region, which are separated through this cyclone separator. Now, there are many advantages for the fluidized bed, and already Professor Hamdulapur has pointed out, it is actually uniform mixing, uniform heat contact is obtained, for which uniform heat transfer, uniform mass transfer, and easy in operations, and simple also, low cost effective, for which it is gaining popularity, or it is advantageous to be used in the industries. And here fluidized bed reactors, where another advantage that heterogeneous catalyst may be used for the heterogeneous catalytic reactors, or for a homogeneous catalytic reactor, the fluidized bed can also be used, and particle size, any size of the particles can be handled in the fluidized bed reactors. So, disadvantage is that when the fluidization is taken place, that means here the because of the bubble movement, particles move up and down, some erosion might occur, erosion of the internals because of the movement of the solid particles may collide with the side wall of the column or the reactor or some internal arrangement. So, erosion of the internals might be there. Attrition of the catalyst particles, the particles also rub against each other, for which attrition might occur. So, that, and because of these small issues, sometimes which issues are found to be small in the bench scale or in the laboratory scale, it may scale up, that is, it may enlarge in case of the scale up or the pilot plant reactors. There are many applications for the fluidized bed reactor, that is one example, Fischer-Tropsch synthesis and phthalic anhydride synthesis, methanol to gasoline. So, almost all type of the industries the fluidized bed technology can be used, or the fluidized bed reactor can be used. And what are things required if you want to design the fluidized bed reactor? That is, the rate constant is required, and also we have to know the tendency of the particles, whether the particles tend to agglomerate or break or erode the internals. So, accordingly we have to decide what type of the fluidization are to be employed, whether the solids sometimes some solid bed materials may be coated with the fluidizing gas or some other catalytic materials. So, and whether the reaction is taking place in the freeboard region or in the main bed region. So, some knowledge information is required before designing the reactors. And also fluidization mainly takes place because of the bubble movement, and this bubble, effective bubble diameter, what should be the size of the bubble, so that we can get the smooth fluidization or the turbulent fluidization, that will be decided. So, depending on the requirement, if the vigorous movement is required, vigorous contact of the solid is required, we should have the bigger bubble diameter. That expressions are there in the hydrodynamic case studies. This will be discussed by the Professor Hamdulapur, or hydrodynamic study 1 Professor Jena also will be taking. So, depending on the requirement, we can decide the it is perhaps 0.711 g dB to the power half. So, that way we can calculate what should be the bubble diameter. So, we can discuss both non-catalytic and catalytic reactors. When we are discussing the non-catalytic reactors, usually in the reactors the three types of the changes occurs to the bed materials, that is particles. The reactant particles may grow in size, may shrink in size, or may remain unchanged in the size. So, this will be the outcome of the this fluidized bed reactor or the reaction processes, and where the rate of reaction of the single particles in the reactor is required to be determined, and also the residence time distribution, how much time the particles is remaining within the reactor, and within the reactor also with which area, that is in the main bed area or in the freeboard region the particle is remaining, that particle size, the time distribution, residence time distribution are also another important factor for the design of the reactors. Now, when the reaction is carried out, suppose A is the gaseous reactant and B is the solid reactant, and B moles of the small b is the number of moles of the solid particles which are used in the fluidized bed reactor. The product may be gaseous product, solid product, or gases and the solid product. Now, when the typical examples for the three situations where the particle size remain unchanged, size reduction takes place, or the size enlargement occurs, the examples are the that is roasting of sulphide ore, reduction of the iron ore, or nitrogenation of the calcium carbide, calcination of the limestones, or activation of the charcoal. Here what happens, the particle size remains unchanged, and solids shrink, that is if the combustion or the gasification of the carbonaceous material, combustion means it is burning. So, the particle size gradually decreasing in also. So, that is the examples of the combustion, gasification are the gasification of the carbonaceous materials where carbon bonds combust. So, their size reduction takes place, that is solids shrink, and growth examples, thermal cracking of the crude oil where the molecule size also increases. So, in a bed of carbon and the production of the pure silicon are the examples for the particle growth during the reactions. So, these three either of these three situations will arise during the reactions. Now, models, when we are going to discuss the models for the conversion of the solids, because solid reactant will be converting to the solid product or the gaseous product or the combination of the gas and the solid product. So, there are two types of the model usually found out, that is the uniform reaction model and another is the shrinking core model. Uniform reaction model means the solid which is reactant which is consumed more or less uniformly throughout the particles, whatever will be consumption will be there, that size will be uniform all along the diameter or the periphery of the solid particles. Now, in the shrinking core model the size gradually slows down, means reduces. So, here diffusion in the first case in the uniform reaction model, it is mainly controlled by the diffusion process, and the second process where the shrinking core model, there the diffusion is slow, reaction mainly controlled by the rate of the reactions. So, just you can see just diagram wise uniform reaction model, or you can say that is first model. Uniform reaction model means from the figure we can see when the it is the suppose solid reactant is there and the gas which is gaseous reactant which comes in contact with the solid reactant, it enters the pores, enters through the, that is it diffuses into the solid particles. Diffuses means it moves to the inside of the particle through the diffusion, that is pores will be there, through those pores the gaseous reactant will be diffusing into the core of the solid particles. So, you can see the when the here when you can see concentration of the solid reactant, it is maximum, it is there. When the gas is moving, it is diffusing through the pores. So, it is covering or the completely the solid pores of the all the pores of the solid particles are completely filled with the gas first. Now, then reaction occurs when the gaseous reactant that fills the all the pores of the solid particles, then they start reacting with the solid reactant, and uniformly at all places it start reacting, because everywhere the gaseous reactant is present, and all the molecules of the solid also in contact with the gaseous reactant. As a result, the reaction also takes place uniformly and concentration decreases gradually. Now, here finally the concentration reduces. So, that means it is reacting and it will be just ash layer or something that will be remaining at the end. So, concentration will be reducing gradually. That reaction moves uniformly, that is the throughout the particle reaction proceeds, because the gaseous reactant fills the pores of the solid particles. Now, here we can see that we can express this as the rate of consumption of B, how much solid particles is consumed during the reaction, that is proportional to the concentration of the A bathing the particles. Bathing means it is uniformly, that is all along the periphery of the particles it will be, or it will be clouding the entire particle. So, that is concentration of the gaseous reactant bathing the particles into the amount of the B left unreacted, how much already consumed and how much left behind, that is. So, the product of these concentrations will be equal means will be proportional to this rate of consumption of the B. So, which we can write in this way: if Ca is the concentration of the gaseous reactant and fraction of the B converted is the Xb. So, we can write that dxb by dt over the time interval dt. We can write that Kr into Ca concentration of A into 1 minus Xb. Xb already Xb is the converted amount, unconverted amount, this is amount of the reactant B left unreacted, that is 1 minus Xb. So, Ci is the constant, as it is the gaseous reactant which is diffusing throughout the particles, its concentration remains constant. So, thus we can integrate this, and we can get this as the 1 minus, that means how much solid remains unconverted, that is 1 minus Xb equal to exponential minus Kr Ca into T. So, here K unit is meter cube of the gas per moles of the gaseous reactant per second time. So, this is the rate coefficient based on the unit volume solid. Now, for the shrinking core model, if you see, as I told that here the in this case the reaction rate is the controlling rate, diffusion is slow, that is because these solid particles are not porous in structure, small pores will be there. So, what happens here, the gas will be moving will be when it will be approaching the pores of these small pores, it will not diffuse. When it just approaches, that means it is in contact with the solid particles. So, it first reaction, it start reacting, the gaseous reactant starts reacting with the solid particles with which it is in contact. That is why it is the reaction front, means low conversion, means first reaction will takes place, gradually the reaction front, when the this layer of the solid particles will be reacting, and after it is converted to the product, it may be solid product, that is ash, or it is the gaseous product. So, the gaseous reactant along with the gaseous product will be moving slowly with this reaction front. So, reaction front you can see gradually it is moving towards the center of the particles. That means these dark layers, these are the product, that is product or the ash layer, already reaction has been taken place. So, here diffusion is slowly, that is the gaseous reactant along with the product gas, it is moving slowly after the reaction taking place. Thus, the last at the last what happens, entire mass becomes the product. That means the reaction front reaches the core of the solids. So, thus you can see here the concentration which is maximum here, because of the reaction here the product is formed. So, now this is become, so it is moving radially. So, thus here this becomes the unreacted zone. This is already reacted, this zone is reacted. Now, here the finally this much remains the core solids. So, this is the shrinking core model, that means particle size reduces, go on reducing. So, thus, so these are the just descriptions. If gaseous product will not form in this shrinking core model, we can just gases A diffuses through the film surrounding the particle to its surface. Gases A penetrates and diffuses through the blanket of the product solid, reaches the reaction front, and then gases A react with the reactant B in the narrow reaction zone. These two will these two steps will be followed when the gaseous reaction product will be forming. If product will not be gaseous product will not be forming, these two steps will not be moving or will not be followed. Now, these models we just discussed some examples also we can see. Suppose a flaking of ash or the no ash forms in this shrinking core model. When we are burning coal in the air, some flaking of ash or the no ash is forming. That means, after the size reduction shrinking core model, that reaction front moves to the center, it is completely shrinking in size, and we can visualize this here. Next slide. Here initial unreacted particle, and in this shrinking core model, when the gaseous reactant comes in contact with the solid particle, initially the reaction will be taking place at this boundary, then it will be gradually moving. So, thus finally, this will be flaking ash will be forming, means the product will be ash product will be forming. Finally, when the gaseous product along with the gaseous reactant will be diffusing further, reaction rate may increase. Finally, the size will be reduced here. So, this is the in this when coal burns, so particle it may convert to means very small sized unreacted particle. That means particle shrinks with time, finally disappear. It may disappear also. This is just examples of the shrinking core models. Now, how to find the right model? For that, we should know that whether the reaction rate is controlling step, or that means if the reaction rate is controlling step or the diffusion is the controlling step. Diffusion controlling step means diffusion is controlling the reaction, means it is the uniform reaction model, and if it is the temperature or the reaction rate is controlling, means it is the shrinking core model. And here the when the reaction rate is controlling, their temperature dependence is very strong, because reactions may be exothermic, may be endothermic. So, it is in the shrinking core model, that is it is the temperature dependence is very strong. When mass transfer controls, the temperature dependence is minor. In case of the mass transfer, temperature difference will be minor, because that is mass transfer will be because of the diffusion, where the diffusion is controlling. But that is why temperature dependence in the mass transfer is minor. So, particle size also has the effect. So, small particles follow the usually the uniform reaction model, because more pores will be available, whereas large particles follow the shrinking core model, where the ash diffusion controlling or the at high temperature, that means reaction rate is controlling, but reaction controlling at the low temperature. So, particle size wise also we can say that if smalls in general, some exceptional cases will be there. In case of the small size particles, we can consider uniform reaction model. In case of the large particles, we can follow the shrinking core model. Now, temperature also independent of the particle size. For the as for the low particle size, we are seeing that uniform reaction model, where it is temperature is independent, and for the shrinking core model, temperature is dependent, because it is the reaction dependent reaction rate controlling, and it is also shrinking core model with sometimes diffusion may, it is not that we can say that the shrinking core model, uniform reaction model are the two ideal states. So, in practice we may have in between, that is combination of the reaction rate and the diffusion also. So, in that case the temperature will be proportional to the shrinking for the shrinking core model with the combination of the diffusion through the product which will be forming during the reactions. So, thus control these examples we will discuss in the afternoon. Controlling resistance to reactions depends primarily on the structure and the porosity of the solid. As I told, if the porous, there also the uniform reaction model will be applied. So, here models for the reaction of the solid cell also we can discuss the fluidized beds. As we find that these are the well studied topics where the solids are transformed into the particles, whether the gaseous reactant is reacting or there or not there. Particles can be rapidly heated, cooled, because of the this is the advantages of the fluidized bed reactor or fluidization technology, where the uniform heating, uniform cooling, uniform mixing is occurring. So, in effect temperature environment can be controlled also easily in case of the fluidized bed reactors. Also, if highly endothermic reactions is occurring according to the shrinking core model, there also driving force is not the diffusion of the reactants throughout the product layer, but heat that is reaction rate is controlling. That means, conduction of the heat will be there through the product layer. So, there also fluidized bed will be advantageous. For fine particles, where the resistance will be controlling, that will be shifting from the heat conduction to the decomposition also. So, thus fluidized bed, all these operations can be easily carried out in using the fluidized bed technology. Both gas and the solids are converted, means whether the gases are the reactant and the solid reactant are there. Sometimes product will be both gas and the solid, and both will be converted to the either to the in the first schematic diagram as you saw, maybe gaseous product only we can get, or gas and the solid, or the solid product we can get also. So, this also so when the that is gas and the solid reactants are used in the fluidized bed reactor, usually the solid will be bathed by the, that is clouded by the gas for the some having the average composition or the concentration in the operating conditions. As a result, here what happens, when it is clouded by the gaseous reactant, the reaction will be slow and concentration of the gaseous reactant will not change much passing through the bed. When it is clouded, and because of that force of the cloud also, it will be moving up. During that movement towards the up, moving towards the top of the bed, reaction does not taking much, slight changes will be there. First, what happens when the cloud is formed, the cloud will be the gaseous reactant which is clouding the solid reactant, that will try to diffuse into it, whether it is porous or not non-porous. That is why, and also that bubble movement takes place so fast that particles also in the fluidized bed, if you have seen, or the some videos we will be showing the next class. So, there we can see the how fast they are moving. So, with that the reaction will be very less also, does not, reactant does not change, the solid or the gaseous reactant will not change much, it will just clouding with the force of the cloud, that is some wake formation will be there. That means wake formation at the bottom some W shape will be there, and the cloud will be surrounding the solid particle with the W shape. So, that with that some it will be that force, it will be moving up. So, thus the reaction does not change much, the reactant does not change much when it is moving upward. When solids are transformed into the product without the action of the gaseous reactant, such as the calcination of the limestone. So, there also both gas and the solids are converted, and mean gas phase driving force in the bed is the variable that changes with operating conditions. The gas phase driving force, as I told, it is the main the cloud formation, which is the gas phase, that is pushing the particles upward directions, and so that it becomes the driving force. That is the accordingly the operating conditions within the reactor also changing, because when much of the cloud formation will be there, bubble formation will be there. So, there the heat transfer will be to some extent it will be reduced, operating conditions may change also. Example, if the feed rate of the solid is low, the concentration of the gaseous reactant in the bed will be naturally, because if the solid is amount is less, the gaseous reactant will be more, it will be more, the thickness of the cloud layer will be increasing. So, concentration of the gaseous reactant will be rising. So, we will be discussing, that is interaction will be 3-step calculations, numericals we will be solving, we will be moving to the catalytic reactors, then some environmental purpose, how to handle the pollutants, that part we will discuss. Some catalytic reactors, if you see here, it can be 3 types of the reactors: bench scale fixed bed reactors, bench scale fluidized bed reactor, and then the pilot plant reactors. Here in the bench scale fixed bed reactors, that is bench scale means it is when you are using in the laboratory level, small unit. So, reasonable estimate of the stoichiometry of the rate constant for the desired reactions to be taking place under the various conditions, what is the temperature, what is the pressure, what is the concentrations. So, with that we can just carry out some experiment in the fixed beds, where the bed material is the catalyst, beds of the catalyst. So, we should have the following information, that is the what is the reasonable estimate of the stoichiometry and rate constant, indication of the possible side reactions, what are the, because before designing, so we should have some background knowledge. So, whether any side reaction will be taking place or not, and various regimes, that is size of the pellets, effect of the catalyst, then the temperatures, effect of catalyst formulation means sometimes some reactant also may act as the catalyst in the latter stages. So, that is whether it is catalyst formation will be there or not, and what are the physical factors which will be that is pore diffusion will be there or not. So, accordingly the rate of reactions and the distribution of the product will be also changing. So, those things we should means one should have the that is the knowledge, one should study all these factors before designing the reactors. So, whether the stability of the catalyst is there or not, and so preliminary measure of this rate of it, whether catalyst is deactivating, at what rate it is deactivating. So, these studies should be carried out also. So, in case of the fluidized bed, bench scale fluidized bed reactors, where fluidized beds are designed for the, or the experiments are conducted in the bench scale fluidized bed reactors. So, we can have the data on the 1 minus XA. XA will be the how much amount of the gaseous reactant is being consumed, and 1 minus XA how much remaining that is unconsumed, versus KTT under various bed conditions. So, with varying conditions you can see how much is consumed, how much remaining unconsumed. So, from the we can get the plot, and effective bubble diameter we can also calculate, then possible secondary reactions, whether it is the fixed bed or the fluidized bed reactor, what will be the side reactions, those things also one should study. Then the kinetics and the activation deactivation rate of the deactivation rate constant of the catalyst, because catalyst sometimes deactivate also, that also whether activity is changing, tendency of the catalyst, sometimes the catalyst also agglomerate or the erode or the break. So, those information properties of the catalyst also should be studied. Now, pilot plant reactors, whether it is fixed bed or the pilot plant, first thing is to bench scale study is to be carried out, then the pilot plant studies, the pilot plant design is to be made, and then we can compare the conversions of this that is reactant, what is the literature says, that is from the theory what information is available, and if there is the good agreement, one can go on designing the pilot plant units. Otherwise, it will be difficult, because second purpose is pilot plant when it is designed to discover the factors or harmful effects or sometimes harmful phenomena which will be unnoticed during the bench scale operations, but these harmful phenomena may be scaled up when we are designing the pilot plant units. Now, the factors usually which because theory sometimes all the factors are not studied or are not reported, but that is that's why we say that it is the some practical gap will be there when we ourselves we design and install, then we may face some difficulties. So, sometimes some unwanted undesired problems may be expected from the experience. So, none of these problems become the evident in the pilot plant. Scale up can often proceed if there is no problem, one can proceed to the pilot plant units. Final purpose will be to get confidence of these steady state conditions, because initially all the reactions will be in the transient conditions when we start the operations. So, objective will be to maintain the steady state. So, that final purpose will to have the confidence to maintain the steady state operations. So, design decisions, that is some bench scale data when it is available, some other factors can be considered for the design of the reactors, that is in the pilot plant sizes. So, what is the use of the circulation systems, bed type, the bubble size, bed aspect ratio, height to diameter ratio, freeboard region, what height freeboard is there, what height main bed region is there, because that also has impact on the reactions, because if the freeboard region is high, reactions may takes place in the freeboard region, with that some of the gaseous product may be lost to the atmosphere. So, distributors, what type of the distributor is considered to support the solid particles, and activity level of the catalyst, high temperature, stability and aging of the catalyst, control of the size distribution, surface of the heat exchangers. So, out of this you can see bed aspect ratio, freeboard region, distributor, selection of the bed type, use of a circulation system, these will be the mechanical type. Means in the fabrication type depends on us what type we should select depending on the particle size and type of the reactions. But sometimes during the operations this may occur, means activity, if catalyst is activity level is not of the required quantity or the required not up to the satisfaction, that will affect the rate of reaction. Again, high temperature stability, sometimes catalyst may be unstable at the high temperature and it may aged also. So, that also these are the during operations the problems might occur. So, for which sometimes catalyst deactivates rapidly. So, that is to be, if regeneration can supply the heat needed by the reaction of a circulation system. If we use a circulation system, it may be regenerated. So, there we can use the circulation system, so that we can have a safe stable steady state circulation systems, and there will be no damage or the attrition or the breakage of the catalyst also. Sometimes the that is bed type as freely bubbling bed with the internals. Freely bubbling means if the bubble formation will be there, it will be moving up along with the bubbles, solid particles will be moving up. When the bubbles will break, particles will scattered and they move in the radial directions. That is why during the fluidization both vertical movement as well as the radial movement of the particles remain. So, circulation systems use the flowing of the solids for the heat control, and also freely bubbling beds are usually used. And sometimes if we want to restrict the movement, so we may use the internals. Means if we want to restrict the radial movement or horizontal movement, we may use the vertical internals. If you want to restrict the vertical movement, we may use the horizontal internals. And also conversion with the internals, what happens? Conversion is limited, and it is recommended that internals be used to achieve the rational scale up. Up to what level scale up is required, and how to reduce the time and cost of the development. Based on that, we may use the select the internals. So, for the vertical internals, vertical tube bundles may be used, or the horizontal internals, and the horizontal bundles of the tubes may be used. When the internals are there, suppose bubble moves in the vertical direction, if you use the horizontal bundles, the bubbles will break, thus the vertical movement will be restricted. So, bed aspect ratio also, there should be the proper height to diameter ratio, that is the aspect ratio. Accordingly, the freeboard main board region will be decided also, and sometimes what happens, bed internals are used and then bed aspect ratio also affected. So, proper what aspect ratio is required, that is to be decided first. Safe value for the minimum aspect ratio should be unit. It is height to bed diameter should be the unit, that is the minimum value. So, we can take more than that also. Freeboard region, that is as I told in the reactor components, the region above the bed is the freeboard region. So, there splash zone means just above the when we are fluidizing, the just fluidization started, the particles just splashed means slightly bed is expanded. So, that zone is the splash zone. So, that splash zone here just above the bed will be the bubbling bed catalyst is entrained above the splash zone. Now, sometimes when we want to when we will increase the flow rate, the splash zone will be overcome, will be reaching the freeboard region. Reaction the catalyst particle if exceeds the splash zone, then reaction will be taking in the freeboard region. Another entrainment means carryover of the solids. Now, during the fluidization, some if the supplied velocity, superficial velocity is more than the terminal velocity, the particles will be carry over or taken out of the bed, that is the entrainment. So, that for that TDH, transport disengaging height also, these are the in the hydrodynamics we will be studying also. So, here in the freeboard region some reactions will take place. As a result, through this TDH the product gas will be lost. So, accordingly we should have a proper aspect ratio, so that the carryover entrainment will be restricted below the TDH, not above the TDH, and freeboard should be below the TDH also. Accordingly, there we can provide the cyclone separator. If it is above freeboard is above the means extending above the TDH, we can provide the cyclone separator, so that solid particles can be separated from the fluid also. Then distributors, as a good distributor is required, which will be supporting the weight of the bed materials, preventing the that is loss of the materials or passing of the materials to the air pipe or the wind box region. So, porous sintered metal, ceramic plates or bubble cap So, depending on the type of the bed materials, we can select the type of the distributor also. Sometimes the high temperature reactions may be required to be carried out, where the we have to see that whether it has the thermal strength or not, and sometimes the distributor may have the thermal expansion if very high temperature, and accordingly we have to select the material of construction also. So, distributor is to be selected properly. Now, for these are the mechanical aspect we discussed, because during the fabrication we have to decide what will be the bed aspect ratio, where the TDH to be located, where the what type of the distributor to be taken. Now, the activity level of the catalyst during the reactions, what is the type of the catalyst we are selecting. During the operations, this phenomena may occur, that if catalyst is poisoned, that is becomes the slow and irreversible, means material loss will be there. Usually we need that catalyst regeneration should be there, so that we can reuse the catalyst. But if catalyst is poisoned, it becomes the reaction becomes the slow and irreversible, and where the catalyst activity also cannot be recovered, and sometimes the there will be permanent lowering of the activity also. It is frequently caused by the small quantity of the impurities in the feed. So, if some impurities is present in the feed material or the bed material, then that also sometimes lowers the activity of the catalyst also. So, thus we have to see that whether the inorganic or organic salts of the metals are used as the catalyst, whether it is inert material or whether it is reacting with the bed material or not. So, accordingly we can select, and sometimes due to the age, again and again use when we are using again and again, the aging will be there also, or very long period it is just kept idle. Due to the aging also, the catalyst may becomes the slow, irreversible, and thus permanent deactivation is attributed. So, it will not help in catalyzing the reactions also. So, fouling also caused by the deposition of the reaction product. Sometimes during the reactions, the products may get deposited on the catalyst also. So, fouling occurs also. So, usually this product is a carbonaceous material, in which case the process is called the coking also. If carbonaceous material gets deposited, means becomes the product carbonaceous material and it gets deposited. So, it will we can say this process as the coking. So, high temperature stability and aging of catalyst, we have to select such catalyst which will be stable under high temperature also, and whenever required we can deactivate that and we can use that also. So, then size reduction, size distribution also to be controlled properly. Achha, within 2 minutes we will finish this, then we will move to the environment part. Time and we are gradually with the time and again uses also break down the particles, or with the bed materials if vigorously that is turbulent fluidization is carried out. So, particles may break down and move the size distribution. Once the bed material particular size, suppose we have taken 0.5 centimeter sizes we have taken, and with the again and again fluidization, what happens, the some sizes will be reduced. So, it may be 0.1 centimeter. So, if the different sizes will be there, then what happens, lighter particles will be moving to the freeboard region, and once it reaches the freeboard region, there is chance of entrainment also, because with the increase of the velocity, these lighter particles may leave the bed also, maybe go out of the bed, that is the entrainment. So, as a result, in the bed becomes the only the particle amount reduces, also size also reduces. So, thus that is that affect the size distribution, or if it is not carried over also it remains. So, more and more fines will be created also in the bed, that is size distribution in the bed also affected. So, this affects the efficiency of the reactions, and also solid recovery also is affected, and also there will be fine due to the entrainment also, loss of fines will be there. There will be shift of the size distribution, because you we calculate the rate of reaction as per a particular size. If size distribution is there, it shifts towards the finer size, naturally reaction rate will be also affected. So, the direction of the distribution moves depends on the friability of the solids. If the broken particles are there, are easy to break and friable particles are there, then the collection efficiency of the cyclones will also be required to be high, or we have to use the ESPs also. So, that way it will become the expensive process also. So, that is why we have to control the size distribution. So, surface of heat exchangers, so they are depending on the how much temperature we need, we may provide the internal arrangement, heating arrangement, cooling arrangement, or the externally outside the reactor also we can provide also, that is providing within a chamber or jacket. So, best to construct the heat exchanger tubes or also to also act as the internals to control the bubble size. So, as I had told, vertical internals, horizontal internals, with that also we can move the we can control the bubble size. Now, pollutant part, if you see as the gases, here we discussed the gaseous reactant and the solid reactant reacting. So, this fluidized bed reactor, although we can use for the solid reactions also, but mainly will be in here we can focus on the gaseous pollutant which are present in the air and affecting our environment. So, we can handle this gaseous pollutant using the fluidized bed reactor. So, because these pollutants has very harmful effects on the health and the environment. The gaseous pollutants which are affecting our health, carbon dioxide, sulfur dioxide, the particulate matter, lead compounds in the air, photochemical pollutions, and the fluorides etc. are also present in the air. So, these things also we can reduce by carrying out the reactions in the using a fluidized bed reactor. Here we can just in the short we can say, because all we know that carbon dioxide is produced as the waste in various reactions. So, here normal sample of air contains about 0.05% carbon dioxide by weight. So, using this suppose we take the bed of the silica or bed of the lime. So, there we can absorb the carbon dioxide also. So, that we can form the calcium carbonate or something. So, that is carrying out the reactions in the fluidized bed reactor. We can convert this gaseous pollutant to another solid product, useful solid product which we may use somewhere, or we may use it as the landfill also. That is similarly solution in the ocean followed by precipitation, utilization of carbon dioxide by green plants also, that we can sequestration we can do also in the use in the photosynthesis, carbon dioxide, carbon monoxide from the fossil fuels. So, these are also obtained, sulfur dioxide which are also products are available in the natural gas, in contrast to the coal, oil which is almost free of the sulfur. Again just some we can convert to, that is carrying out the reactions in the fluidized bed reactors, we can get the that is sulfuric acid also dissolved in water, or the just in the reactions we can react with the here the sulfur dioxide when react with the oxygen or air, sulfur trioxide, then dissolves in the water. So, that we can, or we can combust it also during the combustion, which will be producing sulfur dioxide will be producing, or we can sulfur trioxide will be producing also. So, both sulfur dioxide, sulfur trioxide also we can absorb in water, produce the sulfuric acid, or we can carry out the reactions also. Just one we will discuss, refer to the experiment which we conducted in our lab, it was in the 2015 or something. using the scrubbers and the fluidized bed, we can that is sulfur dioxide also. Limestone reacts with the sulfur dioxide, which will be coming from burning the coal from the fine particles of the calcium sulphate, and which can be carried up in the stock gas also. Particulate matter also another serious pollutant. Unlike this pollutant also, which are already discussed, particles not of the single chemical type, different types will be there. So, here also instead of numerous solid and liquid compounds which will be dispersed in the air from many sources, and so we can take some solid particles. We have to actually first that is analyze it, what are the type of the major pollutant. Based on that, we can take the solid material in the bed, which will be reacting and forming some other solid product. Just fluoride part we can see. Here one of the major hazardous gases pollutant is the fluorine, and its limit is up to 1 ppm. Now, here fluoride is difficult to break down or to reduce to non-toxic forms. So, that is why the exhaust gases which is coming from the aluminum plant or the phosphatic fertilizer plant or the semiconductor chips industries, so polluting the environment. So, those things we can handle using the fluidized bed reactors. And just adverse effects and these sources here. Now, it is not used, but we can use also. This was in the 2015, one PhD student was working on this. So, using this fluidized bed reactor, where the gaseous pollutant was collected from the Vedant aluminum plant, that was collected, and it was passed through this reactor as the secondary gaseous stream, because it is not sufficient to fluidize the material. To fluidize the material, we supplied the air, and it was insulated by providing the insulation outside, because heater was provided inside. The temperature of the reaction was around 700 degree centigrade, sorry 500 degree centigrade. Here the bed materials was selected as red mud we took, because red mud, it is the iron, aluminum, titanium, many metallic components are there. When we pass this gaseous effluent which contains the fluorides was passed through it, and these fluorides which are present in this gaseous component reacted with these metals present in the red mud, that is forming the aluminum fluoride, ferrous fluoride, ferric fluoride, and the thus the level of the concentration of the fluorides in the gaseous effluent was measured, found to be reduced. So, this is the just schematic diagram of the fluidized bed reactor, and use the red mud. So, additionally some aluminum particles also were used. So, to ensure that more metallic particles are present, because we had taken that some small means 5 liter of the gaseous effluent only. So, with that we found that finally we characterized the product gas coming out of the fluidized bed reactor, where it was found to be in the aluminum fluoride and the ferric fluoride. That chart I have not, that is ICP-MS characterized with that we found. So, with this we can say that the gaseous pollutant can be reduced using a fluidized bed reactor. That is, we have to bed material accordingly, we have to select what type of the, we are focusing for what type of the pollutant. So, we have to knowing that we have to select the bed materials. so that that gaseous pollutant can react with the bed material and form some solid, which comparatively handling of the solid waste is easier than the gaseous waste or the gaseous pollutant. So, fluidized bed reactor is a key or the you can say a prime unit to handle the air pollution in the present scenario. With this, we stop here and we will do some numericals in the afternoon class.